The third part of the result is the synoptical evolution. Figure 6 shows the geopotential height in shading and horizontal wind in vectors on 200 helipascal. It shows that Rambia was relatively weak in high levels. From 6D to 6F, we can see, after landfalling, the wind here is much larger than wind here, and the difference was getting stronger. The tropical cyclone was within a divergent zone, which is favorable for the ascending motion as a result. Figure 7 shows the geopotential height in shading and horizontal wind in vectors on 500 helipascal. Here we can see from 7A to 7C that Rambia was influenced by a high-pressure system and another tropical cyclone before landfalling, which made strong convergence in the northeast Rambia, and the strong high-pressure system led to the outflow of Rambia. Well, after Rambia made its landfall, the asymmetric structure of Rambia is even obvious in such large scale in 7D. Rambia was mainly under the control of the high pressure caused by the mid-latitude Rossby wave. Later in 7E and 7F, the high wind area was always to the right side of Rambia, and later rainfall evolution may thus be the result of the divergent here, which could cause ascending motion in lower levels. Figure 8 shows the geopotential height in shading and horizontal wind vectors on 850 helipascal. The influence of the other tropical cyclone is more obvious here. From 8A to 8B, when Rambia was still over the Pacific, it was influenced a lot by the high pressure over the sea and the other tropical cyclone. From figure 8C to 8D, we can find the southeastward flow to the southwest of Rambia was weakened by the other tropical cyclone. This may contribute a lot to the asymmetric structure of Rambia during landfalling. And from 8E to 8F, Rambia got back to a symmetric structure, but was relatively weak in strength. Next is the fourth part of the results. I will use a vertical profile to show the structure of Rambia more clearly. Figure 9 is a vertical wind profile with same longitude across the TZ center. The magnitude of vertical motion is shown in shading, and negative values refer to the upward motion. The vectors combine the radial wind and vertical motion. The black line refers to the location of the TZ center. The structure is of great asymmetric structure all over the landfall period. From 9A and 9B, the south Rambia had weak ascending motion before landfalling, and there shows outward tilt in figure 9A. That may be the result of the influence of the other tropical cyclone. After landfalling, there was limited vertical motion due to the mountain there, while for the north of Rambia, the ascending motion kept intensifying during landfalling. This corresponding to the heavy rainfall there. The ascending motion was much stronger in 9D, and from 9C and 9D we can find a secondary circulation occurred. Figure 10 is the vertical wind profile with same longitude across the TZ center. The magnitude of the radial wind is shown in shading, and the negative values revert to the inflow. The dashed contours revert to the tangential wind. For the south of Rambia, in low level, there was always inflow except in Tenby. That's made due to the other tropical cyclone. In the North Rambia, the tangential wind was always larger because there was not influenced by the southeast flow but the flow from the high pressure system. For the tangential wind is larger here, there must be strong inertial stability and lead to strong upward motion, as mentioned before. Figure 11 is vertical wind profile with same latitude across the TC center. There was strong upward motion in the West Rambia in 11C and in the east in 11B. The asymmetric structure was totally destroyed at this time. This may be because the high pressure system to the northeast and the other tropical cyclone to the southwest, which forced a flow from east to west. Figure 12 is a vertical wind profile with the same latitude across the TC center. The tangential wind is relatively asymmetric in 12B and 12C, which lead to the symmetric upward motion due to the difference in inertial stability. We can notice from the coastline that also other systems cause the outflow in the East Rambia. The land friction contributes to the inflow in lower levels. Figure 13 shows the boundary layer height evolution. It clearly shows that the boundary layer height in the southern part of Rambia kept lifting before landfalling, but descended after landfalling. In the southern part of Rambia, the acceleration of the lifting speed is negative, while positive in the southern part of Rambia. In addition, the height decreased more after landfalling in the east. The difference of the boundary layer height between the northern and southern part will increase with time. Figure 14 shows the boundary layer height evolution, also with the same latitude. It clearly shows that the boundary layer height in the western part of Rambia was extremely high and decreased a lot from 0 o'clock to 12 o'clock UTC. Then the depth caps increased. In the eastern of Rambia, the depth graded. Also, along the radial changed from large to small, compared with the difference of the boundary layer depths in the last figure. The difference between the western and eastern part decreased with time. Figure 15 is the vertical motion distribution on 850 hPa. From figure 15A and 15B, we can find that before landfalling, there was weak wave number 2 structure. After Rambia made its landfall, we can see from figure 15C and 15D clearly that the southern part of the wave number 2 structure was almost not changed, while the northern part enhanced apparently, especially for the ascending motion in the north. The strong ascending motion is corresponding to the heavy rainfall shown in 3F. Next, we will move to the summary part. Although Rambia was a relatively weak tropical cyclone, it weakened slowly after landfall and led to flooding. This corresponding to the results of Yu in 2017. The mountain and the friction of the land caused a convergence to the south of Rambia, which led to the precipitation to the south of Rambia at first. But as tropical cyclone moved inland, the TC moved much closer to the mountain and the flow could not climb the mountain, and thus the rainfall was mainly concentrated to the north of Rambia. During landfalling, the convergence increased in the northern part of Rambia due to the friction increase and orographic influence, and thus enhanced the upward motion. Although the high pressure system to the northeast contributed to a lot. At this time, there was enough water vapor supply also from the ocean surface. Rambia was also influenced by other systems, and led to its divergent structure and asymmetric structure. And the strength did not decrease rapidly. This may be a favorable condition for heavy rainfall, and this is corresponding to the research before. Then is the sixth part. This will be about the future work. In future, I will use WRF model to simulate Rambia and find more structural details about this tropical cyclone. Numerical study and a complete mechanism is desired. After that, another obvious rainfall evolution of Rambia during its turning will be discussed. Also, WRF model will be used to find out the mechanism. Thank you for your listening.